Let's go ahead, guys, and look at this. So I'm going to go pictures first. Before we go to the pictures, I'm going to tell you that our topic is going to be the cooling system. How is the cooling system put together from a mechanical and electrical point of view? What do I need to know electrically when I put it together? What are the quantities, electrical quantities that we need to pay attention? Which article applies to it, and so forth. With this, I found it very easy, guys, to go directly into this picture. So this is how the main how the main cooling system in a building is put together. There are main components, very important components, guys, in any HVAC system. This is the cooling system only. You're looking at a cooling system only. The most important one is number one right here. They call it the evaporator. The goal of the evaporator is to take the air from the room, the hot air, right? Capture the hot air through the liquid inside these bars that you're looking at. Take the hot air from the room, capture the hot air in the liquid, bring it back outside. Make sense? So what they do, guys, for the evaporator is the section of the HVAC equipment inside your building. If you have in residential terms, this will be inside your furnace. That piece will be inside your furnace, right? The air, so any question, guys, about the evaporator? It takes the air from the room, capture the heat from it, take it into the liquid. This is mechanical. And capture the heat in the liquid and take the heat outside. Any question about this? I'll show you where the electrical interface in a second here. This is just the mechanical system. So for this one to work, the first thing electrically needed is I need a blower. So what do you need? Here's our interface. You need a fuse disconnect, right? So you need to power. Here's our electrical interface component. I need a blower, a fan, to blow the air through this coil, right? So that's, can you guys see the red thing is going to be my electrical interface. So you have a fan, and I need to power the fan. Cool? Okay. Now, what we did already, for my friend, we have the evaporator capture the hot air in the room, the heat into the coil. So when it captures it, now it takes it back to number two, the compressor. Can you guys see that? It captures it from the air through the coils here into the, as a liquid, bring it back. They call it, then it becomes, the liquid becomes, when you bring the liquid here, becomes, they call it low pressure gas. Because of the heat, the liquid turns into low pressure gas. That's the refrigerant inside it. Low pressure gas. Now we captured all the heat. Well, we captured the heat from the room. Inside the gas, which is the liquid, which is now gas, take it to the compressor. The second thing the compressor is, now here's another electrical component that I need to power. Okay, here's a disconnect, and here's a fuse, and here's my interface. Can you guys see where my electrical interface with this? Another compressor, which is a motor compressor machine put together that I need to power. It's called a compressor. The job of the compressor is to compress that low pressure gas and convert it into high pressure gas. Compress, every time you compress, you reduce the volume. By reduce the volume, the temperature will go down, and then you have a high pressure gas coming out of the system. The refrigerant, instead of low pressure gas, becomes a high pressure gas. Cool? That's the job. So compress from low pressure coming into high pressure. Now, then they send it into the condenser. So what's the job of the compressor? Is just to compress that low pressure gas into high pressure gas. Then it continues in the pipe all the way to the evaporator. Number three is the evaporator. The evaporator, guys, has also another electrical component here, fan. And that fan most likely will be powered from the same system here. I have a fan here. So what they do, now this high pressure gas is still have, the heat is still captured on it. Not all the heat is lost. The heat is still captured on it. What they do is they blow huge amount of air through these coils. Can you see all these coils? A huge amount of air. What the air does is it carries the heat from the high pressure gas and throw it to Mother Nature. So if you go next to air conditioning unit, guys, and you look at the evaporator the condenser moving the air, the fan, you're going to see that it's very hot right at the top of the air conditioning. Very hot air coming out of it. So all the heat that comes out of this room, we put high pressure, we pressure it to make the system work better. We send it through these coils, and then we blow big blower right through it. So it takes the heat out of that high pressure coil and throw it into Mother Nature, outdoor. Now, by doing it this way, guess what happened? When you blow all the heat out of it, now what comes, it turns from gas into what? Liquid. Now you get yourself into a liquid. That liquid is very cold. If you touch it, it's cold because all the heat has been gone out of it. And it brings it, now it pumps it all the way back to the evaporator. The evaporator throws air into it again. It captures the heat, and it continues to do this refrigerant cycle. So if I'm to say, this will be where you're going to have right here, this cycle where it's going to be the cold. This is cold here. That's your cold cycle. Coming out of the room is your hot cycle. Hot cycle. Okay? That's how they show them, blue and red. So the cold, you put this liquid, you put it in these coils, you blow the air again, it captures, the liquid captures the heat by converting itself from liquid into gas. That's how they capture the heat. And this cycle continues to go on and on and on forever. Any question, guys, about these three major components of the whole cooling system? The cooling system. This is the cooling. There's no heat here. There's a purely cooling system. The last component that we don't interface with is the valve right here. Can you guys see that? This is number 4. They call it the valve. This will regulate based on the temperature how much of this liquid will enter the evaporator. It regulates based on the temperature. There's a temperature sensor here that regulates valve up, 4, less, regulate how much of that cold is going to enter the evaporator. Any question about these 4 components of the cooling system? Now this is, guys, all this that you're looking at could be in one unit. A good example of this, Dustin, window air conditioner, right? When you have a window air conditioner, all what you're looking at is one unit. Or it could be split unit. A good example of this is residential. You have this one inside your furnace, this coil, if you have a central air. This will be inside your furnace, and this will be, we all know that, where they say AC, sitting outside, which the condenser and the high pressure and the compressor are sitting outside to throw the hot air out. Or it could be rooftop unit. Rooftop units are very similar, guys. Rooftop unit could be one package rooftop units right on the top and throws air, hot or cold air. They add the heat to it too. Or it could be a split unit rooftop unit where you have these 2 pieces, condenser and compressor, in one location, and the evaporator inside the building. So you can have a lot of packages for them. A lot of packages. Okay, when you go to a bigger system, and I'm going to stop right here because it will come into it. Now this is smaller system. You go to a bigger system. This baby, they start calling it chiller. This guy becomes a chiller. The compressor here becomes a chiller, chilled water. And this coil here becomes inside air handling unit. Can you guys see that? It becomes on a bigger system like Dunwoody. It's an air handling unit. Becomes an air handling unit inside the air handling unit. And this baby here, the condenser, become cooling tower. Cooling tower. Cooling tower. Now the air handling unit and the chiller, most likely they will be inside the building. The cooling tower will be sitting outside. And instead of refrigerant pipe that they're pulling, because refrigerant, you can't pull refrigerant, guys, 500 feet away inside the whole building. Instead of refrigerant in a smaller system, what they do is they chilled water. Yeah, in a larger system, they chill the water. So they bring the whole cycle happening here, they chill the water here, and then they send water to circulate into the cooling tower, as well as the condenser with evaporator, in a slightly different. It's not exactly the same way, but similar. Yes, sir. Radiator takes, it's a hot and blow the air out of the heat, right? That would be probably the condenser. Yeah, the radiator will be equivalent to the condenser because you're taking heat, you're blowing the heat out, right, to cool it. So that's exactly what everything here is hot, and you're blowing air to get the heat out. That would be equivalent to the condenser in terms of function. Any question, guys, how the mechanical? Now, electrically speaking, I need to power the fan inside. I need to power the compressor and the fan outside, and I need to provide a control system. That's what I want to do. Okay, we don't care about the piping between them. We don't do that. The mechanical guys, our friends, cousins, do all this mechanical equipment, and we provide a feeder to feed their system. I need always ask about the evaporator or the air handling unit. The chiller, remember the chiller and air handling? We don't have air handling. We have air handling unit and chiller in the project. We don't have a cooling tower. Okay, so that's basically the major components of a cooling system. Any question, guys, about this? When we go to a bigger system, we'll touch into the chiller, air handling unit, cooling tower combo. So that's basically really the major part of that one. Talks about the coiling, rooftop units. Hot air goes up, cool comes here. This is where the gas in and gas out, how the system is put together. Cooling water, hot water. Refrigerant, when you use the water as your refrigerant, getting into the system. And a couple of these guys, how the compressor, what they do for the compressor, the low pressure gas guys, right over the motor, so it cools the motor. That's why the compressor motor is a special type of motor. Okay, I'm going to stop. I'm going to come all the way to this control. So we know how the system is put together mechanically. I want to go to this one, guys, and look at how the system is put together in a control, from a control point of view. I want to remind you, this is a packaged cooling system. I can't read that one, so I might have to look at this. What they do, guys, is I have to look at it here. Well, I can zoom into certain things here. Okay, so here's all the legend that you're going to be using. The first thing is my CM. Can you guys see the CM here? CM is my compressor. Here's my compressor. Can you guys see where my compressor is? I need an overload provided by manufacturer. CS, the control relay provided by manufacturer. The only thing I provide electrically is that 3-phase disconnect and the fuse, as well as the cables. Can you guys see that? Oh, that's all what we do. We provide a feeder with a disconnect and a fuse unit. Okay? Everything else is inside the unit. All the control is inside the unit. I want to bring you guys to this area first. This one is this particular one. Can you guys see this coil right here? CS coil. This CS coil control the compressor. Can you see where it says CS here? Control the compressor. So the most important thing, guys, is see where it says the overload here. If there's an overload condition, this compressor will never work. If the temperature gets so hot, this compressor will never work. If the pressure goes so high or so low, it becomes a bomb. You're compressing air, guys. You can change it into high pressure that this thing will explode. This branch here is giving you the safety. The top is the safety. Safety, very important. You're messing around with Mother Nature. Pressure, every time you mess with the pressure, you're creating a bomb. You know what I mean? So this branch right here is basically for your control system. For your control system. So if any of, yes, everything is internal in the machine. Yeah. And then, can you guys see the CFM? CFM stands for the evaporator fan. That's the fan that's going to be blowing air on the coils. So this one, when the way it works, can you guys see when the control relay here is energized? Here's my thermostat. It really is. You put yourself in cool, and you put it in auto. Then the thermostat will call right in here. Will call for cool. And then there is no low pressure situation. The CR will energize. When CR is energizing, this control relay 2, CR2 will energize. Now CFM is running, as well as the compressor is up and running. There is EFM2. EFM is evaporator fan. Evaporator fan will also run.
EFM, if EFMR is energized, then the EFR will energize by this relay. Can you guys see this relay? So anyway, there's a lot of control system. I don't want to spend too much time on it because we really, our interface with it, unless you're doing troubleshooting, which we do schematics here, but you guys are not.
The only interface that you need to do with is that class 2 control circuit. This circuit here is a class number 2 control circuit, thermostat wire. Can you see 3 wires going from the thermostat directly into the chiller, right?
Into the condensing unit. So that's the first interface, wiring in the field. And then you come over here, obviously, and we're going to provide a disconnect,
A fuse disconnect for the system. That's also an interface plus the feeder. So I need a feeder, and I need disconnect with fuse most of the time. It could be without fuse.
and then the whole control system is packaged together. A lot of safety involved in it. There's one little thing, guys. This is typical for residential. One little thing. Can you guys see where it says way at the bottom?
Can you see what it says? 2 heat pump.
Now this also can give you heat. This is a package that gives you heat, cool.
So from the same thermostat, if you turn this one into heat, it will energize your heat pump or your boiler or whatever system where you energize your gas and get you heat. The same thermostat.
Those additional fuses in the lower right-hand corner of the diagram over internal.
Let me just go back here. Yes, everything inside is internal.
Everything here is internal, packaged. Yep, absolutely. Our really interfaces will provide a fuse and a disconnect for this unit.
These are packaged together, manufactured equipment. You provide a control wire for it and a circuit.
So if those blow in the air conditioning guy,
Yes, you have to go. If it's not working, you're going to go trouble.
If these blow because the compressor fans are blowing, these overcompression device blows, you have to go change these fuses. There's fuses for these, fuse for this system, and there's a fuse for the whole system right here, for the whole package.
Absolutely. Any comments, guys? Any question about the control system?
We provide a power circuit at the top, a disconnect fuse, plus a class 2 control circuit. How the system work together
Is
an interesting, as I said, the first branch is safety. The rest is to make sure when you call for heat, you energize the compressor as well as the fan.
you want to energize the compressor and the fan. If you have high pressure situation, the last thing you want to do is pump more into the compressor and explode it. So there's a lot of safety issues. Any comments, any questions? So that's, again, this is just for simple system. It gets more complicated, guys, as you go higher.
This unit, in a commercial building, guys, they use rooftop units. Rooftop units could give you, if you can see, says this is to the power, to bring the power. This is the control. What they do here is they bring, it's a complete unit, condenser and all this good stuff. They condense. It can come in 2 sections, the way I understand it. You can have a split section, or you can have a packaged one, old packaged system. So where you can basically cool the air and blow the air down here. See how it blows gets the hot air and blow it, keep taking the air in and out and cooling it and bring it back, cool and bring back, cool and bring back. Or you can have the evaporator sitting somewhere down here. You can have evaporator sitting down at the bottom and piped all the way to the unit. It's like 2 things. You can either have them all in one package, or you can have split. The evaporator can be down, my evaporator down, and my condenser and compressor up on the roof. That's rooftop units, one single package, or you can have split package where you can have the condenser sitting down, the evaporator in this area, and the condenser as well as the compressor are sitting on the roof.
Commonly used, you're going to hear them with smaller commercial building use rooftop units. Bigger commercial building use chillers, cooling towers, and air handling units. Chillers, cooling towers, and air handling units. Okay, the key point is, what's our interface, guys? Our interface is we need to power. Can you guys see how we're powering here?
and we're also powering here, and we might get involved in providing a wire for the control of the system.
That's our interfaces. We don't set the equipment. We power the equipment, and 99% of the time we don't control the equipment. The HVAC guys will control the equipment. Any comments? Any questions on the rooftop unit system? Okay, so that's okay. Now, article. Okay, that's good. Maybe I can look. Rooftop units, guys, and chillers and all this good stuff, especially equipment. There you go. Systems like this have a nameplate. HVAC equipment has a nameplate. Everything in the NEC code book, NEC 440, article NEC 440. If you go there, guys, it will tell you, because this is special system, the cooling system, we want you to use what the manufacturers are giving you right on the nameplate. For example, when we size the conductors, here's a nameplate, very easy. I can run this system in 2 voltages based on how I wire it. I can run it in 208 or 230, 60 hertz, 3-phase US, right? This is okay. Compressor rated load amp. Rated load amps, you can give you rated load amps. So if you have minimum, so you have the rated load amps. They take all the full load amps of all the equipment, guys, and give you one value. This is like full load current for the motors, equivalent to full load current for the motors. Locked rotor current. This is very important when sizing disconnects. We size the disconnect based on the locked rotor current. So you have a locked rotor current. You want the disconnect, guys, to be able to interrupt the locked rotor current of this system. Then moving down, it's split into condenser and evaporator because it's a packaged unit. Here's the full load amp for the motor of the condenser and for the evaporator. For the evaporator, this is a whole package. There's also kilowatt. There's strip heat there that heats it to make the system work too. They added it. We really care. In this case, we only care about this value here when we design right here. Everything else is internally wired. Minimum breaker circuit selection current. This is called minimum circuit ampacity. That's how I'm going to size my conductors. Conductor size. That's how I'm going to size my conductor directly from this value, minimum circuit ampacity. Okay, so if I have, here's my disconnect, here's my fuse, here's my unit. This is a HVAC cooling unit, and this is my feeder. So take this. This feeder must be, let's just say the system is 208 volt, okay? 208 volt goes with the higher the voltage goes with the lower the amp, so that would be 58.6. So this is 58.6 amps. Okay, now the disconnect, my disconnect, my fuse. Let's talk about my fuse. My fuse, guys, maximum fuse amps is 60 for both of them. Or hacker, if you want to use a hacker or circuit breaker, is also 60. So I'm using a fuse here. I'm going to use 60 amp fuse. Okay, I size my fuse. My disconnect, 1.15 multiplied by the rated load amp, 25. Most likely that will get you 60 amp, right? 60 amp disconnect. It's more than 30, right? Is it?
We just got done telling us it was a locked rotor current that we had to consider.
2 things you consider. For your disconnect, you consider 2 things. So 1.15 times 25 equal 28. This would be, well, I have to go to 60 because of the fuse anyway. So this is, you size it based on 1.15, and then you have to use, and I'm not going to do it now, then you also have to make sure its size, I'll show you the table that we use for, also to handle size based horsepower-wise. Horsepower-wise, it's sized to handle 164 locked rotor current, 164 locked rotor current, horsepower-wise. There are 2 things, guys, and I'm not going to do it today. We will do calculation on that one. When we size a disconnect, we size it based on 2 things. Number one, the full load amp. Number two, the horsepower interruption. The full load amps, we size full load amp based on two things. The full load amp here, like I did, and also the locked rotor amp. Whichever gets us a bigger horsepower, we have to stick with it. Whichever gets us a bigger horsepower, we have to stick with it. Okay, so most of the stuff that you need from Article 440 is directly from this nameplate. Directly from this nameplate. Any comments, guys? Any questions about that? We will do calculation on that one, guys. How to size them and so forth, but this is just a quick intro, basically. Okay, maximum locked rotor current for certain motors, 440.51. I'm going to go directly into here. Okay, so here's how this table, guys, is used to size the horsepower of your equipment. So let's go, Chris. Let's go one more time to this one. Can you see? Can you guys see? Can everybody read the locked rotor current 164? Everybody can see that 164, and I'm running it at 208, right? I'm running at 208, 164. Cool. Remember the word 164. Now let's go size the disconnect for it. It's three phase. So if you come over here, here's 164, three phase. This table 430.250. I want you guys to 164. Can you go all the way down to 164 under 208 because I'm running at 208, 164. 164, here's 140, 164 is right here, right? So I have to go to the next standard because 164, there's no 164, I have to go to the next one. If you reference it, that will give me a horsepower of what? 10. So this motor has to be 10 horsepower rated based on the locked rotor current, based on the locked rotor current. We also size it based on the full load amps, and we choose the size the largest. So based on the rated load amps, let's just say, guys, based on rated load amps, we came up with 15 horsepower, and based on locked rotor current, we came with 10 horsepower. Which one do you think we're going to be using? The largest. Disconnects are sized two ways, horsepower and amps. Horsepower, we use this table to size based on the locked rotor current, and we use 430.250 to size based on the full load amp, okay? And we choose the largest. Then we size the full load amp based on 1.15 times the rated load amps of the motor, and go up if it's not a standard. And again, we will get back to these guys and do a lot of calculation on these. We will do calculation on these, locked rotor current for different equipments. So that's sizing the horsepower rating of the equipment. Okay, so the same. Well, actually, let's do it one more time. I want you to, if you guys don't mind, we use 58.6. Can you guys see where it says 58.6? 58.6, okay, and 164. Okay, let's go size the horsepower based on 58.6. We sized this, we did the calculation for this, and we came up with 10, right? Based on, oops, 10, Chad. Based on this, we came up with 10 because of that, right? That's based on locked rotor current. Okay, so remember that one. We came up with 10. Let's go based on full load current, size it based on full load current. It was 58, right? So go to different table now. This is, you guys are familiar with this table because we use it with motors. Okay, this is full load current for three-phase motors. It was 208. It was 208. So here's my system is 208. It was 58, right? Oladipo, it was 58.
Yeah.
So I can't find 58. I have to go to 74. Based on this, what is the horsepower rating of my motor? Rated load amps.
We have 59 down to
Did they go down?
58 is less than 50. 59.
Say it again.
59, it's okay.
59,
Yeah.
because it was 58. Thank you.
Yeah.
58. So if I go to this, based on this, what's my horsepower rated based on rated load amps of 58 amps? Based on this, 20 horsepower. And based on locked rotor current, it was what? 10.
10 horsepower. 10 horsepower. So a lollipop. Does it take a rocket scientist to tell you that you're going to use the largest?
That's it. We use the largest. We will do calculation for these. I promise you. So disconnects have to be rated based on locked rotor current and full load amps. Okay, so that's this is full load amps for single phase and three phase motor. You guys are familiar with that, and that's our system. Any question, guys? How the whole system is put together? HVAC equipment, yes sir.
Can you go higher in horsepower?
Yes. Rating, but you will be throwing money
Yeah.
out the window. Yep. For example, if a disconnect is rated for 10 horsepower, would it handle 25 horsepower? Yep, absolutely. Same thing. If a disconnect is rated for 60 amps, would it handle a disconnect? Just a disconnect, not a fuse. Would it handle a 30 amp? Would it replace a 30 amp? Yes, as long as you don't have fuse in it. The fuse is a different story. You can't go higher on the fuse. Disconnects. If you need a 20 amp here and you put 30 amp, can't handle 20 amp, you overkill. Okay, so that's basically what I wanted to show, guys. And let me just see if I missed something on my PowerPoint presentation. That's really what I wanted to show on this system. So we talked about the cooling system, refrigeration. Here's the four evaporator, compressor, condenser, and the valve. Talked about this system, the evaporator, the compressor, the condenser, expansion valve. They call them hermetic compressors, guys, because the motor is cooled. The way they do the motor for the compressor is actually cooled because of that cooling system. So they can abuse this motor more than any other motor. That's why the code deal with hermetic compressors motors different than any other motor, because they have a cooling system that, so they can, long story short, they can abuse it. Okay, so that's what I wanted to say about that one. Okay, the control system. This just talks about what we're doing in the building. Okay, in the NEC code book, in the book, guys, there's a couple of terminologies that you have to get used to. Rated locked rotor amps. This is the locked rotor amps. This is remember how we size the disconnect based on this one. So if the motor doesn't start, the compressor doesn't start, that's the highest amount of current that you can pull if the motor is locked, doesn't start. Rated load amps or current, this is equivalent to the full load amps. It's full load amp of the equipment. Minimum branch circuit selection current. What they do is, because this is a special system, they run them under experiments, guys, and they give a value. They call it minimum branch circuit selection current that you can use to select your fuses and circuit breakers. So it's similar to the rated load amps. Maximum overcome protection device, that's where you put your fuse and or your circuit breaker directly. Overcome protection device selection, and disconnect means rating. They might sometimes give you a disconnect means rating. So all these are terminology. We looked at them, guys, in the nameplate. The most important thing is really the locked rotor current and the rated load amps or rated load currents. So these are important because we size conductors between them. There's also minimum circuit ampacity that we size the conductor based on this one directly. Minimum circuit ampacity. So these are a few terminology that they have definition in the book, guys. You can read them at your own leisure. Disconnect means, here's where we said the disconnect means, guys, the NEC code book, you have to have 115. Look what they do. They do 115 multiplied by rated load current or branch circuit selection current, whichever is larger. So if you have a rated load current 50 and branch circuit selection current 53, use the larger of those. All these are on the nameplate. Disconnect shall have rating equivalent to the table. Remember how the disconnect rating that we looked at based on horsepower? That's where this tells you to rate it based on amps as well as horsepower. Okay, special equipment. All right, terminologies. Okay, current. controllers, all these controllers, guys, we don't get involved too much in sizing them. Packaged tons versus amps, all these are sized in tons. What we did, guys, when like rooftop units, say 50, 100 tons, these tons have a tables that translate the tons into kVA or kW. And when we deal with the tons versus kW, usually we deal with the mechanical engineers who tell you this is 500-ton chiller. How am I going to convert it into kW? There's a factor. Every manufacturer has a little factor that they use, and it converts it directly in kW. If I have kW, I can assume, say, an 85 power factor and size it from there. But most of the time, guys, at least my experience and a lot of people, when you have a chiller, and especially chillers, you will have on the nameplate everything that you need to size for that chiller. Minimum circuit ambiguity, overcome protection device, and all this good stuff. Okay, so that's basically what what I wanted to go in terms of this chapter. Any question, guys, about the whole system, how the system is put together? I want to remind you, a bigger system with chiller, boiler, air handling unit, and cooling tower interface, we will be doing it in the industrial building. It's very similar to this, very similar. It's except they circulate chilled water and hot water instead of chilled refrigerant. Any comments, any questions? Okay, so that's basically the interface with it. The calculation, Chris, we will do calculation on multiple, like it will tell you if you have a multiple compressor in one feeder, you have to take the rated load amps, add them up, multiply it by 1.15. All these calculations, you guys will do a few of them next quarter. Okay, that's all we have. Thank you.